So welcome. So this is static equilibrium and elasticity notes, and there's going to be like 3 different bits we're going to do today. I guess there's going to be one bit on center of gravity. There's going to be another bit which is in static equilibrium, where we use torques to solve things, and then the final little bit is going to be on elastic properties of solid, which is really material science. And there's a interesting area there for study. Let's talk about center of gravity. We've talked about center of mass before, so let's remind ourselves about that. Let's do that and go back one. So we talked about center of mass before, and center of mass was simply take each discrete particle's mass and multiply by its position, its displacement from an axis, add all those up and divide it by the total mass. And we also did a IJK version of this, and we also did a distributed mass version of this. That's the triangle and all that kind of stuff. Well, we're not going to go there. We're just going to stick with discrete particles for this bit. And all right, what's the difference between the center of mass and center of gravity? Center of gravity deals with weights. So if you like, that's the weight and that's the weight. So they don't in the book, as far as I can see, but center of gravity equals the sum. You could say the weight times the position over the sum of the weights. You could say that, actually. That would be quite a simple way of remembering it. And the weight, of course, is not the mass. I think the thing they're concerned about is you'll just multiply the mass by 10, because we've got it so drilled into us that W equals mg and g is always 10. And if the g is the same for every particle, this is a trivial problem, because it's just the same as the center of mass. It's when g is different for different particles. And when does that happen? And that happens kind of like if I have a planet and I have a structure, and the structure is large compared with the planet, then because this is close, there'll be a big weight on a given kilogram. And because this is far away, there'll be a smaller weight on a given kilogram, because the gravitational field is getting less and less and less and less and less. So although the masses of that kilogram and that kilogram are the same, the weight of them is different. And so the center of mass, would be the middle. But because the end that's near the planet has more weight than the end that's further away from the planet, although the center of mass would be there, our center of gravity will be there. And so we get this kind of weird situation. This happens, we see it an awful lot with big structures like astronomy structures, galaxies, solar systems and the like. Actually, there's a thing with the moon where the moon always keeps the same face pointing towards us. And what we say is that the rotation rate of the moon is the same as its revolution rate about the Earth. But they look back at old pictures, and it's been exactly the same for at least 600 years. They've got pictures of the moon, looks the same structures. So what on earth is going on? And when things are perfectly aligned, you're either incredibly lucky, which is like so lucky it's unbelievable, or there's something pinning it down. There's some reason why it stays the same. There's some law that's keeping the thing in check. And there is in this case. What you do is you have, because you have the Earth and the Moon, what you get is a kind of a stronger gravitational pull on the bottom, on the bit of the Moon facing us, and a weaker gravitational pull on the bit that's on the other side. And you tend to get a situation where the center of mass and the center of gravity don't quite line up, because it's a small difference, but there is a bit of a difference between the gravitational field at the front and the back. And so it's a bit like a pendulum, where this thing, kind of like will always tend to settle at the lowest point. And so you end up with the same face. This pins it. If the moon kind of tends to want to go like that, this will pull it back round until it's lined up again. So you see these effects, subtle effects in different places. Centre of gravity is located at the centre of the mass as long as the object is in a uniform gravitational field. So we're not going to put it in a uniform gravitational field. 2 kilogram particle is located at +3 on the x-axis, and the 6 kilogram particle is located at +8 on the x-axis. So we have a 2 kilogram particle at 3, and we have a let's have a look, a 6 kilogram particle at 8. And he says the gravitational field strength. Well, there's the, if you like, G is a vector. So G is, and I'm drawing that the wrong way around, that's a big G. That's a littler G because it's further away. And we know that G is equal to -12 over x. So as x gets bigger, that fraction gets smaller. It's always negative because it points in a negative direction, but gravity gets smaller. So where on the x-axis is the centre of gravity? And what we say is, well, let's have a look. X centre of gravity is equal to, and I'm going to try my new way of writing it down, the weight of each one times the position of each one over the sum of the weight of each one. That reminds me that it's the sum of the mass of each one times the G for each one times the position of each one over the mass for each one times the G for each one. And, I'm sorry, I'm doing it backwards. This is the centre of mass. We'll swap this around. Centre of grav. If I have space. I might not have space. I'll just rearrange things. So centre of gravity. So then this equals, well, our first mass is 2. And our gravity is -12 over x. I don't think that negative sign makes a difference. I'll leave it in for the minute while I think about it. And then that is 3. And that's a sum, so we're going to add these guys up together. And the next one is 6. And that's -12 over 8 times 8. I'm sorry, that was 3 should be in there, shouldn't it? Because it is 3 meters away. Over, and this is going to be the weight of the bottom things, which is -12 over 3 times 2 plus 6 times -12 over 8. As I say, I'm not sure about the negative signs. I think it all cancels out in the end. We'll just push it through. So let's look, those two cancel. So that's going to be -24 added to, and those two cancel. So that's going to be -72 over, and then this is going to be, well, now they don't cancel, do they? So that's -24 over 3 added to -72 over 8. Man. So -24 -72 would be 96 -96 over. And then we can do this by cross multiplying, or I can just take my calculator and work it out. Sometimes I think we're just better off taking our calculator and working things out. So I'm going to go 24 divided by 3, enter, added to, because we're supposed to add them, they're both negative, bracket, 72 divided by 8, enter, and I'm getting 17 on that, -17. That makes sense? 7, 6, 8, 8 eighths are 64, and 9 eighths are 72. So that's going to be 8 and -97. Yeah, that makes sense. And so that equals -96 over 17. So 96 divided by 17 equals, that's going to be 5.6. Does that make sense? We've got to be between the 3 and the 8. And we're going to be, well, we're going to be a little bit, well, actually it's interesting. It's 5.6, so that's 3, 4, 5, 6, 7, 8. And we're at 3, 4, 5, 5.8. We're kind of like there, okay? 5.6. Let's just compare it with our centre of gravity. So our x, centre of mass is equal to the sum of mi xi over the sum of mi, which equals, I look at my diagram again, it's 2 times 3 added to 6 times 8 over 2 plus 6. So that would be 6 plus 48 over 8, which equals 54 over 8. 5 8s are 40, 6 8s are 48. So 6 8s are 48. And carry 6.75. So the centre of gravity is 6.75, which is there. The centre of gravity, centre of mass is there, and the centre of gravity is there. So it has shifted it towards the source of the gravitational field. Yeah. Does that make sense? It's just another equation. You know, it's kind of like skills are just the same skills. It's just another equation. Static equilibrium. So we're going to spend a bit of time on this. We've said that the sum of the forces in any direction either equals ma or equals 0. And if it equals ma, we're dealing with Newton's second law, and there's going to be an acceleration because you have a net force. And if the sum of the forces balance each other, then there's equilibrium. There's no acceleration. And so the classic way they get you to think about this is they say, well, okay, here's a situation. Here's a tree trunk. It's been felled. It's laying on the ground. And one set of workers kind of grab hold of it and they're pulling it in that direction. And the other set of workers grab hold of it and they're pulling that direction. And they're pulled just as hard as each other. Are we in equilibrium? And you say, yes, we're in equilibrium because the sum of the forces vertically equals 0. Vertically meaning up and down my page, not vertically in the room. So nothing happens. Well, you know, nothing changes. The velocity doesn't change. If it's stationary to begin with, it's stationary at the end. If it's travelling at 1,000,000 miles an hour to begin with, it's travelling at 1,000,000 miles an hour at the end. Remember, we're travelling at 1,000 miles an hour because of the rotation of the Earth. So we're talking about changes in velocity. But then people say, well, hold on, that's not quite true, though, is it? Because what's going to happen is we're going to get a rotational acceleration because these two forces, although they are along the same line, they are parallel to each other. They're not directly on one line. So it's not sufficient to say the sum of the forces equals 0 for equilibrium under all circumstances. No acceleration. We've got to say there's two conditions for equilibrium, really. There's the sum of the forces equals 0, but then in order for this to match, if we think about it, this force will cause the thing to turn in a clockwise direction, which is a negative torque as far as we're concerned. And the other force will cause it to swing in a clockwise direction, which is also a negative torque. So the sum of the torques about that turning axis do not equal 0. because they're both causing a counterclockwise direction. So for true equilibrium, we have to check on our forces on any given line, and we have to check on our torques about any given turning axis. Okay, so two conditions for equilibrium. And then what we do is we kind of set up a whole bunch of problems where you need to use the sum of the torques. They're designed so that you've got to use the sum of the torques. So we say the location of the axis does not matter. So remember this where we had, say the traffic light in equilibrium. And we said, well, it doesn't matter if you talk about that axis or that axis or that axis or that axis or that axis, because it's in equilibrium in all axes. Well, now we have a turning effect. So let's take a case where it is in equilibrium. So here's my pole, and I have a upwards force, and then say I have two downwards forces, so that these balance out. And what I say is, well, if I take my turning axis around there, I get a clockwise torque and a counterclockwise torque. This has no torque about that axis because it's in line with it. But it doesn't matter where I take, as long as I'm parallel to that first axis, it doesn't matter where I decide to take my turning axis. I'll get the same answer. So just as in the statics case, it doesn't matter which direction you did your axis to resolve your forces along. Now it doesn't matter which axis to resolve your torques about. Doesn't matter. So that's interesting. It means that I can change where my axis is as it suits me. And as with the statics, I think we learned that there's better directions than others. If I have several forces and I want to ignore a force, I can put my axis at 90 degrees to that force to ignore it. We can do the same kind of thinking with this, where there'll be several places I can put my turning axis for my torque. And some are, although mathematically they're all equivalent, they'll all work, some are strategically better than others for making the problem simple. And so that's the skill we're going to learn. So we say, let's take this potato, and let's say that we have two forces acting on it, and they're acting at some distance from the center of mass. So there's the center of mass, and we have two forces pulling. So one of them is causing a counterclockwise torque, we'll call that positive, and the other is causing a clockwise torque, we'll call that negative. And we can say that if two forces are acting on an object, then we can say the total torque is equal to torque 1 plus torque 2 plus torque 3 plus torque 4 plus torque 5. And we add them up. And if it's in rotational equilibrium, the sum of the torques will equal 0. Well, that means we've got to have positive and negative torques. So what we say is counterclockwise torques are positive. And I always remember that by saying, man, I'd have done it the other way around. But because we're going to, this kind of ties in with cross product type stuff, then it turns out no, if it's a counterclockwise torque, it's positive, and a clockwise torque is negative. Clockwise or counterclockwise seems easy, but that's often what trips people up. So you've got to be really mindful of that. There's three classic circumstances that we look at. One is, I don't know what to call this. Balanced beam, I suppose, is the best thing. Sometimes, I think if you look back at the homeworks, it might be called a seesaw, which is what I learned it to call it when I was growing up. S-E-E-S-A-W, I guess. And then in the States, they tend to call these things teeter-totters. So, and this is one of those things where, especially if you're a foreign language speaker, if your first language was not English, and you get into a test, and there's a word like that you don't know, then you've got to ask me, because I don't want to know, do you know colloquial American? Now, if it's a technical term, like if you said to me, well, what does this thing called impulse mean? I'm not an English speaker. I'd say, yeah, no, this is a technical term. You've got to know it, But if it's a colloquialism, I don't want you to be stuck there with a colloquialism. So don't be shy, just ask me. And if it's a technical term, I'll say, hey, it's a technical term. If it's not a technical term, I'll gladly tell you it. So just I'm trying to encourage you about that. So I call that, I'm going to try and remember to call it a balanced beam, but sometimes, it'll be called a seesaw or a teeter-totter. And then this is either a plank against a wall or a boom and a mast with a sheet or something. And then we have a ladder against a wall. And there's also, sometimes you see, in the book you see things called gondolas, the window cleaning gondola. And I used to ask questions about that. I don't ask so many questions about that. And we're doing these three so that, if we were to look at this, in principle we know how to do it. What we don't know is we don't know how to do it quickly. So we don't know how to do it complicatedly. We don't know how to do it, a complicated system efficiently. And that's what you learn in statics, and that and a whole bunch more. It's an entire course on this kind of stuff. So, but let's just get the principles down. So the best way to do it is let's do some. So it says a seesaw. See there I used it. Seesaw is balanced. A 5 Newton weight is located 4 meters to the left of the fulcrum. So the fulcrum, that's a technical term. That's the balance point. And we have a 5 Newton. 5 Newton, I just gave you the weight. I didn't give you the mass. I gave you the weight. I could have given you the mass. Unless you're told otherwise, it's, in the Earth's gravity, so it's going to be 10 meters per second squared. It's like it's in the room. 10 newtons per meter. It's like it's in the room. And this is going to be 4 meters. And then here we have a 15 Newton weight. So we're going to do a 15 Newton weight. And where is it located? So I'm going to say X meters. Now, let's make that bigger so that we know, that's the big force. Okay. And I've been around a bit, so I know that X is probably going to be less than 4 meters because, it's balancing. Okay. How do I approach this? I say the sum of the torques about a turning axis. And I've got to tell people where my turning axis is because it can be anywhere. And I'm going to pick the most obvious place to pick is there. So I put a little dot there so that I know, and I put the same dot there so I know. So I try and be clear about where my turning axis is. And that equals 0. So then I say, okay. So I'm going to have, let's have a look. That's going to tend to tilt me in that direction. So it's going to be 5 times 4. Now they're at 90 degrees to each other. Remember torque. Remember what torque is. Let's remind ourselves. Torque is F dotted with D, which equals magnitude of F, magnitude of D, sine the angle between them. And if you like, my D is that vector for this guy. So this is my thigh. So it's 90. Sine of 90 is 1. But that's what I'm doing. And that's going to be a counterclockwise, so that's positive. So there's the first thing that catches people out is they think that the sine of the torque comes from the sine of the force. So because the force is pointing downwards, they want to say it's a negative force, so that's a negative torque. But both forces are pointing downwards. So you cannot determine the sine of the torque from any particular rules about the sine on the force. You've got to determine the sine on the torque by is it a clockwise tending torque or a counterclockwise tending torque. And for this next one, it's going to be, well, it's going to be 15 times x. And that's going to be making it go in a clockwise direction, which is negative. And that equals 0. This must sum to 0. Because it's a seesaw, not spinning round faster and faster and faster. It's just balanced there. So then we get plus 20 added to minus 15x is equal to 0. So 15x is equal to 20. So x is equal to 20 over 15, which equals 1.33 meters. Oh yeah, that makes sense. It's much shorter than 4. Turns out 3 times the amount of weight gives you 1/3 the amount of lever arm. Okay, not bad. It says that the turning axis doesn't matter. So let's satisfy ourselves with that. I'm going to put the turning axis through the 5 Newton one. So I'm going to draw this again. Let's make my turning axis here. Some other talks about this turning axis equals 0. Well, take your first force, your 5. There's no distance. We'd have 5 times 0. Well, that's, whoa, hold on. And then we'd say plus, we'd go 15 times, what's this distance? What distance should I put down? Is it 15x? What is it? What's my lever arm for this force about that turning axis? This force about that turning axis. What's the distance? What's the perpendicular distance? I don't know that. That's from the previous thing. We're starting again. So what is that distance? Right, I mean, tell me an expression for it. What is it going to be? It's going to be, who's going to do it? Do we count the 4? 4. Do we count the x? 4 plus x. Okay. But that can't possibly equal 0. It can't possibly equal 0. There's something not right here. Well, it's true. That has no lever arm, so let's get rid of it. Forget that, because, 5 newtons goes through the turning axis. It's got no effect. So, oh, hold on. I have missed a force out. Because if it's 5 newtons down and 15 newtons down, the sum of the forces equals 0. There must be 20 newtons up. I just blew that off completely. And that's one of the problems, is you probably taught, if you were taught these things earlier, they always put the turning axis through the fulcrum. And they ignore the fact that there's a force through the fulcrum, and the reason why that force has no lever, has no turning axis, is because the lever arm is 0. So in a way, they pick a point which is doing something very subtle to their calculation without telling you about it. And so if you try and do something that's more general, you find you can't do it, because it's like, whoa, I didn't know I was cancelling out a force by putting my turning axis through it, but that's what I was doing. In that first example, I ignored my 20 Newton force. I could ignore my 20 Newton force because I put my turning axis through it. That was a very significant thing. So I've got to realize what we're doing. So in this case, all right, I'm going to ignore the 5 here. And so now I have this guy here, and this is going to be 20 times 4. Now, is that That 20 is causing it to go in a counterclockwise direction, so that's positive. And this 15 is getting it to go in a clockwise direction, so that's negative. Now that makes sense. My torque caused by my 15 newtons is a negative torque. My torque caused by my 20 newtons is a positive torque. Add them together, I get 0. So I get 80 plus minus, I've got to multiply this out, minus 60. 15 times 4 is 60, and then minus 15x is equal to 0. So 15x is equal to 80 minus 60 is 20. So x is equal to 20 over 15, which equals, let me just check I did that right. That's going to be 20, that goes in a counterclockwise direction, which is positive, and then I have my minus, and that is 15 times 4. Yep, that's right. That's going to be minus 60, 20, that's going to be 20, and then that's going to be minus 15x. So 15x equal to 20, so that's going to be 1.33 meters. So x is 1.33 meters. Same answer. Got by a completely different way. And you could put your turning axis, let's just for the fun of it, let's say we have this, where we have 5 newtons, turning axis 20 newtons, 15 newtons. I want to measure x again. But my x is from there to there. X is from there to there. And this is 2. And that's 2. So I just divided that 4 up and put the turning axis in the middle. Say the sum of the torques about my turning axis equal to 0. So it's going to be 5 times 2, and that's going to cause a counterclockwise torque, which is a positive, added to 20 times 2, and that's going to cause a counterclockwise torque, which is positive, added to 15 times x plus 2, and that's going to cause a clockwise torque, which is negative, equals 0. So plus 10 added to plus 40 added to minus 15x added to minus 30 is equal to 0. So 15x is equal to 10 plus 40. Let's turn that to the other side. Yeah, 10 plus 40 minus 30, which equals 50 minus 30 is 20. 15x is equal to 20. X is equal to 1.33 meters. So again, we get the same answer. We always get the same answer. I don't even have to be on this line. I can be above it. I can be wherever I like, and I will get the same answer, provided I do the math right. But you can see, I hope, that, you can make the problem really involved, or you can make the problem really straightforward by picking your axes well or badly. Cool. That's the first level. I want to ask you a question. have a meter ruler. The meter ruler has a mass of 6 kilograms. I hang from this meter ruler a 2 kilogram mass, and let's say this 2 kilogram mass is 5 centimeters from the end. Where do I need to put my fulcrum for equilibrium? Well, there's a strategic choice here. And one choice is, well, I'm going to divide the ruler into 2. I'm going to take the bit of the ruler that's to the left of the fulcrum as one object. I'm going to take the bit of the ruler that's to the right of the object as the other object. So I divide the ruler into 2 objects. That's the hard way. The easier way is to say, it's a ruler. It's got a center of mass, center of gravity as far as for the weight. And it's in the middle. So I reconfigure this and I go, oh, I have a 2 kilogram mass, which is at 5 centimeters. I have a fulcrum. Let's giving that. So that's going to give me 20 newtons. I have a fulcrum, which is going to give me upwards force, and that's going to be at X centimeters. And I have a 6 kilogram mass, which gives me 60 newtons, and that's going to be at 50 centimeters. Because it's going to be in the middle. Center of gravity is going to be in the middle of the thing. So we can say the sum of the torques about our turning axis equals 0. And let's put our turning axis here. Why not? Let's put our turning axis there. So I don't need to worry about it. It's trivial. I just add them together and get 80. Let's just put our turning axis there. And then I say 20 times, oh, actually, I'm not going to do that. I'm going to make it actually even easier. I'm going to, so the numbers, I can make the numbers simple. This is going to be 80 newtons. You see why it's 80 newtons? Because you've got 60 and 20 pointing downwards, so 80 must be pointing upwards, yeah? I'm going to put my turning axis here. Why not? So the sum of the torques about that turning axis equals 0. So that's 20 times 0.05. I can actually get away with it, put it in centimeters, but let's, to some extent it's a bit of a bad habit, so 0.05. And that's going to be in a clockwise direction. That's a negative bit added to. And then I have my 80 times x. And that's going to be in a counterclockwise direction, which is a positive torque. And then I have my 60 times 0.5. And that's going to give me a clockwise torque, so that's negative equals 0. So minus 10 times that would be 0.5. That's going to be 1, isn't it? Minus 1, 20 times 0.5 is 0.5 times, yeah, minus 1, added to ADX, added to minus 30 is equal to 0. So ADX is equal to 30 plus 1, which equals 31. So X is going to equal 31 over 80, which equals 0.39, 0.39. So you put this distance here from the beginning would be 39 centimeters from the start position. Can you see how it's very easy to make that into a horrible problem that would take you a long time to solve if you're not careful, if you try and divide it into 2 bits? You can do it. It still works. But then the amount of mass is not 6, it's a proportion of 6. You've got to say, you know, it's going to be x over 100 times 6 for one side, and x times, what is it? And it would be 100 minus x over 100 times 6 for the mass on the other side. It's easy to say, I can't possibly do that. You can. It's just that it takes a long time. But if you just recognize the fact that the center of mass is the center of mass, and you can symbolize the whole body by that one point in space, then the whole of the effect of the ruler is basically represented by that point there with all the weight there, and it works just fine. Oh, but I need to. Has everybody got this down? Because I need to erase it. I should have gone to a new page. Okay, I'm going to start erasing. So let's have a look. How are we doing for time? Not so bad. Okay. So now this is the next level of difficulty, which is a mast and a beam. So we have a 4 kilogram uniform 6 meter long horizontal beam. So there's it's going to be 40 newtons. It's from the middle, so that's going to be 3 meters from there to there. I know that because it's 6 meter long. Supported by a wall. So there's my wall at one end, and a rope at the other. The rope makes an angle of 35 degrees. So the ropes have tension in them, and that's 35 degrees. And then what is it about this wall? I mean, if this was a smooth wall, that mast would just slide out. It's not pinned, it's just pushing against it. So imagine there's got to be a frictional force which goes upwards, FF, and there's also going to be a normal force, FN. Those won't even mention, and they won't be mentioned. That's the trick next, is we just have forces that you've got to know about. And if I had a pin through this, there'd still be a force upwards, which I could call the frictional force, and there'd still be a normal force. So it doesn't matter if it's pinned or not. There's going to be a frictional force and a normal force. But you can see it, I think, most clearly if you have a smooth wall. You can just imagine if there's not an upwards force, that end is just going to slip out. You know, there's got to be an upwards force there to get any kind of equilibrium. How many unknowns? How many named unknowns do I have on this diagram? I got 1. I got 2. I got 3. It's wants to know what the tension force is, wants to know what that one is, but not the other two. So I need three equations. Well, do I? Maybe there's a way I can think more strategically. What I learned with forces is, if I want to ignore a force, I draw my axis at 90 degrees to it. Because there's no component of this force along this axis. That's the way of getting rid of one force, yeah? What I learned with torques is, if I want to ignore a force, if I want to ignore the turning effects of a force, I put the turning axis through it. Isn't that what I learned previously? Is that what we're talking about? When we moved our turning axis, some forces had no effect on our equation. Not because the force didn't exist, but because the turning effects of the force did not exist. Imagine rather than pulling on the handle of a wrench, you pull on the bolt. There's no turning effect from pulling on the bolt. You've got to pull at a distance to get a turning effect. So there's got to be a lever arm, and if you make the lever arm 0, there's no turning effect. So my advice, what you do here is you take your pen and you put it on one of the forces that you don't want to deal with, and you took that and you put it on the other force that you don't want to deal with, and where they cross you put your turning axis. So they cross here, so if I put my turning axis there, I don't need to worry about FF's torque, because there is none about that turning axis. And I don't need to worry about my FN's torque, because there is not any torque about that turning axis. And the only thing that creates a torque is T, and that's what I want. So I say, oh, well, this is the sum of the torques about my turning axis equals 0. That's going to be 40 times, I want the perpendicular distance, and that 40 is vertically downwards, and that thing is horizontal, so that's 40 times 3, and that's causing, what is that, a clockwise torque or a counterclockwise torque? Put your finger on this guy, the turning axis, and rub your finger along where that 40 is, and ask yourself, which way will the page go? The page will go clockwise. People have trouble with that. It sounds trivial, but people make mistakes on that. So that's clockwise, and so that is negative. Now, the only other force that's causing a torque is this T, but I've got a decision to make. Is it it can't be T times 6, because T is not perpendicular to 6 and 6 is not perpendicular to T. It can be that force times the perpendicular distance, or it can be the perpendicular force times the lever arm. And I, just looking at this, I would sooner say that that is T sine 35. I'm breaking this up into components. One of the components goes through my turning axis. I can ignore it. This guy here. So I say, oh, plus my force is T sine 35. And my perpendicular lever arm is 6 meters long. That is making a counterclockwise torque, which is positive. And that equals 0. So components are back again. Components, if you got components, it's a skill that keeps on giving. If you didn't get components, it just keeps taking away. If you still can't do components, you need to see somebody, me or somebody else. But you're just going to keep paying price for it. It's just going to keep on coming. So that's going to be minus 120. Added to 6 sine 35. 6 sine 35. So that's going to be 3.44 plus 3.44 T is equal to 0. So T is equal to 120 over 3.44, which equals 120 divided by 3.44 equals, and I'm getting 34.9. Now notice, let's actually do one. I'm going to introduce a bit of paper here. So let's take that same problem. What was this, 6 kilograms? Was that right? 60 newtons? I can't remember. 40? 40? Yeah? And this was 6 meters long, that's right, yeah. And then, of course, I have to put my thinking cap on, and I have to recognize, oh, let's do that. Didn't go, did it? Yeah, okay. That I have a FF and I have a FN. Find FF. So I don't want tension this time. I want to find the frictional force. So where would you put your turning axis so that you did not have to worry about the tension and you did not have to worry about the Fn? They're the two that you want to get rid of. Where would you put your turning axis? You'd put it here, wouldn't you? Because you'd put your pen along the tension force and you'd put your pen along the Fn, and where they cross is there. Yeah? Okay. And you would say, oh, FF times, well, from here, that's 6 meters away. That's going to be a clockwise torque, which is negative. Well, sorry, we're saying the sum of the torques about my turning axis equals 0. So that's the FF taken care of. Added to, and we still have this 40. And that 40 is only 3 meters away. And it's causing a counterclockwise torque, which is positive. So that sums to 0. So 6FF is equal to 120. So FF is equal to 20 newtons. And have we got that? Yeah. And let's say we decide we want to do, I want to do find Fn. Oops, Fn. Where would you put your turning axis to find Fn? You want to put your pen down on the FF. You want to put your pen down on the tension. They're the two you don't want. So where would you put your turning axis to find the Fn? Put your pen down on that bit, put your pen down on that bit. That's where they cross. We say the sum of the torques equals 0 about that turning axis. I look here and I say Fn, and that's going to be, oh, that is an opposite, and I know the adjacent. Fn times, well, let's have a look at this. That distance there, oh, almost got it finished. That distance there, tan 35 is equal to that distance there, let's call it y. That distance there over 6. So y is equal to 6 tan 35. So Fn times 6 tan 35. So that's that bit done. And it's going to be we're talking about the Fn, so the Fn is going to give us a counterclockwise, which is positive. Added to, now the only other force we've got here is this 40, so that's 40, and you know, if you push this back, that there is the same as that there, so that's 3 meters times 3 meters, and that's going to give us a clockwise torque which is negative equals 0. So Fn is equal to 120 divided by 6 tan 35. 120 divided by parentheses 6 tan 35 parentheses equals 28.6. So we can ring the changes so much on those questions. The same setup, and I can ask you a bunch of different things. If I wanted to be long-winded, I could ask you for the coefficient of friction between the mast and the beam, and you'd have to fit on the wall. You'd have to figure out what your Fn is and what your Ff is, and figure it out from using that. So, awful lot of problems can be figured out. I can ring the changes on this so easily. Okay, so don't learn one and not learn the approach, not the actual problem. Cool. Let's pause there. Let's